Hi everyone. So to piggyback off of yesterday's lesson, today we are going to be talking about how we can color images. And it was pretty easy when you think about each little pixel, each little square just being on or off. So it was a 1 or a 0 value in there, and it literally was the number 1 or 0. Now I want you to think about what would you do if you had the color blue, and what color blue. And so take a moment and think about how many shades of the color blue you can name. How many do you think there are in total? You're going to be doing this completely on your own. So if we were in class, we'd be talking about this and making a list of this on the board, but it's not necessary. You know, you can think of many, many, many shades of blue, I'm sure. So as we continue today, I want us to keep thinking about whether there is a limit to the number of shades of blue in the world and whether a computer is capable of displaying all of those shades. And if so, how and how do we get to that? Okay, we're going to see how this relationship between analog and digital plays out in the world of color. So to remind you again, analog is when you have a continuous piece of something. So it could be if a drawing that you put the pencil on paper and that pencil just continues straight along, but that's going to look very different when pixelated. It's also very much the same thing as when we go out into the tents and we hear the music playing in another tent, and that too is considered an analog version of the music. But if we have to record it, it is broken up, and it would no longer be considered an analog. So you're going to be able to play with the pixelation widget again, but this time you're going to use it to make your own color blends, or gradients we'll also be calling it. After each level, I want you to check your work with a partner. You can be doing that, but you don't necessarily have to. I know that it's hard for you to reach out to people when you're not on campus, so that's fine. So let's continue here. Okay, so the pixelation widget, you're going to see in the pixelation widget that you have different colors, and the colors, first you're going to have the width, the height, the number of bits, okay? And then you have these colors down here, and we'll talk more about that. So in levels 2 and 3, you're going to type in a unique 3-bit code for each pixel, and that's going to produce a total of 8 different colors. And then in levels 4 and 5, you're going to make 4 different shades of blue, followed by 4 different shades of green, using 6 bits per pixel. Okay, and that's the red row is going to already be done for you. And then when you get to level 6, this time you're going to be using 9 bits per pixel, which will make 8 different shades of green and 8 different shades of blue. So it's the same theory as lesson 7. So lesson 7 was really when we were dealing with black and white, but the more pixels we had, the more specificity we could have in the way the image looked. It's a similar concept when we're thinking about the more bits we have inside one of the pixels, the more different numbers we can represent. And the more numbers we can represent, the more color variation we can have, because every single color in the world of computers has a different number assigned to it. So you need very large numbers when you're thinking of colors, because there are so many colors, so therefore you need so many bits. And so each pixel, yesterday we only had 1 bit. It was either a 1 or a 0. It was 1 place value. But now, because we're going to have to be thinking about bigger numbers for various different colors, we are going to need bigger bits. Okay, so then when level 7 and 8, is where you're, level 7 contains samples of various color gradients, and you're going to choose a section from one of the images, and you're going to try and make that sampling. And you're going to attempt to reproduce the sample gradient as best you can in level 8. Obviously, you could spend forever trying to get it exact. You don't have to, but you're going to do your best to get it close to where it's at. And you're going to think about what happens at each level of creating a digital color image, and think about binary. I kind of said a little bit about it. So layers of abstraction. Again, go back to how do you make pizza, and what are all the different levels of making a pizza, right? So as we saw in the last 2 lessons, the digital version of images we produce differ from the original analog images. Analog images change smoothly and continuously. With digital images, we are limited by the number of bits we use. The more bits even if we use a lot of bits, we can still only represent a finite number of colors, and a gradual color change can only happen discretely through a finite set of pixels. And if we look at this chart, we have the digital image layer displays the digital approximation based on a sample of analog image. So, and then we have the different layers all the way down to the binary layer. Okay, so if you could picture it, it's like here you have your ones and zeros. Here you have your graph paper, for lack of a better word. Here is, how many, this is going to be how many bits you have and how many bits you have inside of each pixel. And it just gets more specific as you go along. So. All right, and we'll watch this video really quickly.
Hi, my name is Lamore Freed, and I'm an engineer here at Adafruit Industries. And this is where I do engineering and design, and I design circuits for fashion and music and technology.
My name is Federico Gomez Suarez, and I'm a software developer with Microsoft Hack for Good. And I look into using technology to help us solve some of the big social problems of our times.
You may have heard that computers work on ones and zeros, or you may have seen scary looking visuals like this. But almost nobody today actually deals directly with these ones and zeros. But ones and zeros do play a big role in how computers work on the inside.
Inside a computer are electric wires and circuits that carry all the information in a computer. How do you store or represent information using electricity?
Well, if you have a single wire with electricity flowing through it, the signal can either be on or off. That's not a lot of choices, but it's a really important start. With one wire, we can represent a yes or a no, true or false, a 1 or a 0, or anything else with only 2 options. This on-off state of a single wire is called a bit, and it's the smallest piece of information a computer can store. If you use more wires, you get more bits. More ones and zeros with more bits, you can represent more complex information. But to understand that, we need to learn about something called the binary number system.
In the decimal number system, we have 10 digits from 0 to 9, and that's how we've all learned to count. In the binary number system, we only have 2 digits, 0 and 1. With these 2 digits, we can count up to any number. Here's how this works. In the decimal number system we're all used to, each position in a number has a different value. There's the 1 position, the 10 position, the 100 position, and so on. For example, a 9 in the 100 position is a 900. In binary, each position also carries a value, but instead of multiplying by 10 each time, we multiply by 2. So there's the 1's position, the 2's position, the 4's position, the 8th position, and so on. For example, the number 9 in binary is 1001. To calculate the value, we add 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Almost nobody does this math because computers do it for us. What's important is that any number can be represented with only 1s and 0s, or by a bunch of wires that are on or off. The more wires you use, the larger the numbers you can store.
With 8 wires, you can store numbers between 0 and 255. That's 8 ones. With just 32 wires, you can store all the way from 0 to over 4 billion. Using the binary number system, you can represent any number you like. But what about other types of information, like text, images, or sound? It turns out that all these things can also be represented with numbers. Think of all the letters in the alphabet. You could assign a number to each letter. A could be 1, B could be 2, and so on. You can then represent any word or paragraph as a sequence of numbers. And as we saw, these numbers can be stored as on or off electrical signals. Every word you see on every web page on your phone is represented using a system like this. Now, let's consider photos, videos, and all the graphics you see on the screen. All of these images are made out of teeny dots called pixels, and each pixel has a color. Each of the colors can be represented with numbers. When you consider that a typical image has millions of these pixels, and a typical video shows 30 images per second, and we're talking about a lot of data here.
Every sound is basically a series of vibrations in the air. Vibrations can be represented graphically as a waveform. Any point on this waveform can be represented by a number. And this way, any sound can be broken down into a series of numbers. If you want higher quality sound, you would pick 32-bit audio over 8-bit audio. More bits means a higher range of numbers.
When you use a computer to write code or make your own app, you're not dealing directly with these ones and zeros, but you will be dealing with images or sound or video. So if you want to understand how computers work on the inside, it all comes down to these simple ones and zeros and the electrical signals in the circuits behind them. They are the backbone of how all computers input, store, process, and output information.
Okay, everyone, that's that. Please go through the different requirements and what is being asked in Code Studio for our next class and be ready with that. Thank you.